Hi, my name is Jim, and this is AC Circuits Part 2, and my concern is that some of your calculations may lead you to believe that Kirchhoff's voltage laws are dead on arrival, and that's not the case. So let's look at a different example here, and maybe we can figure out why some of these voltages seem to be in violation of KVL. So the circuit we're going to start with has three components in it, an L, an R, and a C. And anytime you have an energy storage component like an L or a C in series with an R, the maximum phase angle can be 90 degrees. But when you have more than one, like an L and a C, you can exceed 90 degrees, and we're going to see that a little bit later. So what our mission here is to find the voltages across all the components and verify KVL, and that verification is in a PDF file that's in the folder for this. It's done in circuit simulation software, and if you can see by examining the instantaneous voltage rises and drops that the voltages around the loop are equal to 0, or the sum of the rises equal to the sum of the drops. So we have an inductor here at some frequency that has 2K ohms of inductive reactance, a capacitor with minus J 1.5K of reactance. And if we were to plot this on a Z diagram very quickly, we'd see that the capacitor here is down negative J territory, the inductor is up in positive J territory, and then the real component, the 800 ohms, is on the real axis. So first order of business, as usual, is to find Z total, and we're just going to add up the terms here. We have a real 800 ohms, and the J2000 and negative J1500 are like terms, so we can add them together, and that gives us a total impedance in rectangular form of 800 plus J500. So basically where we would be sitting here would be somewhere around here for the sum of the L and the C. So if we want to get this in polar form, because we're going to be wanting to do some division a little bit later, we just use a standard formula, square root of the real squared plus the imaginary squared, inverse tangent of 500 ohms, which is the positive J500, divided by the real, which is 800 ohms. And that gives us a total impedance in polar form of 943 at 32 degrees ohms. If we go further with this, we're going to be using voltage divider. We need to convert the rectangular form of the capacitors and inductors in the polar form. So I've done that here. Z capacitor, so this is the impedance, is equal to negative J 1.5K, which is the same as 1.5K at negative 90 degrees, and there should be an ohm symbol behind that. The impedance of the resistor, well, that's pretty easy. It's 800 at 0 degrees, and the only reason I'm putting 0 there is I want to see something in the numerator with an angle on it. And finally, the impedance of the inductor is J2K, and that ends up being 2K at 90 degrees ohms in polar form. So once we do that, you can see that these rectangular to polar conversions are very simple for pure imaginary parts, and for pure real parts we can proceed. So first let's find the voltage across the capacitor, and that's this guy, and that's going to be from node 3 to ground, and these are the node names here, and you'll be seeing these again when you look at that phase plot. So VC is equal to 10 at 0, and that's the source voltage, times, in polar form, the impedance of the capacitor divided by the total impedance, just like before, and that comes out to be 15.91 volts at negative 122 degrees. So the 15.191 exceeds the supply voltage. So that's kind of different. Next we have the voltage across the resistor is 10 at 0, our source voltage, times 800 ohms at 0 degrees. And it's divided by the total impedance, again 943 at 32 degrees, so that comes out to be 8.48 volts at negative 32 degrees. And then finally we have the inductive voltage, which is 10.0, and in the numerator we have 2K at 90 degrees divided by the total impedance again, which gives us a whopping 21.2 at 58 degrees volts. So you can see we've got some very strange things going on here. So I asked the question, is KVL violated? And at every instant in time. So we took these three waveforms, which I cannot draw here, that's why they're in the diagram, and took vertical slices of time and added up the instantaneous voltages of the source, of the drop across the inductor, the drop across the resistor, and the drop across the capacitor. It would be equal to 0. So KVL applies, it's just instantaneously at all points in the circuit. So while we're this far, let's go on and kind of sketch things out a little bit further for review purposes. Let's find current here, and I'm not using phasor notation with the bars or anything. There's distance and direction, it's a phasor. So our source is 10 at 0 degrees volts, and we're going to divide that by our total impedance, 943 at 32, which gives us 10.6 at negative 32 milliamperes. So if we wanted to double check, if you will, VC by pushing a current through it, we could say that it's equal to the current times the impedance of a capacitor, again in polar form, and that comes out to be the same as the voltage across capacitor is 15.91 at a negative 122 degrees volts. So if we look at a Z diagram of this, an impedance diagram, as we're going to see again, this is just a little bit clearer than what I had on the other page, is the inductive reactance is sitting up here at J2K, capacitive reactance is negative J, 1.5K, and then the resistor here is 800 on the real axis, and when we combine the like terms again, we get J500 inductive, because in a series circuit the bigger reactance wins, so to speak, exactly opposite of a parallel circuit. 800 degrees connect the dots, and the hypotenuse here is going to be 943 ohms, and the angle is going to be 32 degrees. So if we want to plot the current, again, without guessing at it, we need to break it down into rectangular form, and we do that the way we've done everything else before, by using the cosine operator to find the real component and the sine operator to find the imaginary component. So if we do that, we see that the real component of the current is 9.0 milliamperes, and the imaginary component of the current is negative J 6.2 milliamperes. So the net circuit is inductive, and I is lagging the source voltage just like it's supposed to in an inductive circuit. So if we wanted to plot the voltage phasors, and keep in mind there's no scale here, but it looks something like this. The source voltage is 10 at 0 degrees volts, and that phasor would bring us out to about here. The capacitor voltage is sitting in at 15.91 volts with 122 degrees sitting down here. The inductor voltage is 21.2 volts at 58 degrees sitting here, and then finally we have the voltage across the resistance, which is 8.48 volts with 32 degrees sitting between it and the real axis. So when you're dealing with R, L, and C circuits, you can get some strange numbers, and some very interesting things happen when the absolute value of the inductive reactance is equal to the absolute value of the capacitive reactance. And that's a special case, and that would be a series resonant circuit. And all kinds of interesting things can happen with that, say like tuning in a radio. So that's about it for part 2 on the AC component, and thank you for watching.